One of the major things, I think, of my work over the last several decades is the realization that black holes play a very large part in the evolution of galaxies. And this was not realized 30 years ago. Generally, people thought of massive black holes at the centers of galaxies as being some sort of ornamental bauble that is right at the center, like the fairy on the Christmas tree. But what it is it appears to be, is something that controls the whole evolution of the gas in the galaxy and therefore of the appearance of the galaxy. It affects the star formation and everything else. Black hole produces so much energy and so much momentum in its radiation that it can actually control the whole behavior of the gas in the whole galaxy, or the center of a cluster of galaxies. When I talk about clusters, I'm not talking about the whole cluster, I'm talking about the central 10% of it. But nevertheless, that can be controlled by a black hole at the center of the central galaxy. And the ratio of the size of the region that's being controlled to the size of the black hole is roughly the ratio of the size of the Earth to the size of an orange. So we've got something the size of an orange controlling something the size of the Earth. The mass ratio is 1,000 to 1,000, whereas the mass ratio between the Earth and an orange is much, much larger.
How do black holes occur?
Actually, what happens is you get a star which is more than, say, 30 times the mass of the Sun, evolves, and it lasts only about 1 million years due to fusion of energy, hydrogen to helium to carbon to oxygen and so forth. And you can't go any further than iron and getting energy out of such processes. And eventually the core of the star reaches that state and collapses inwards. Gravity takes over and collapses inwards. And if the star and the core of the star is massive enough, it can collapse down and form a black hole. There's nothing can stop it. So the core of the star, that's the inner few solar masses, collapses inwards, while actually there's an enormous energy release as it collapses inwards. There's a lot of release of gravitational energy, and that's going to fling the rest of the star away, and that's a supernova explosion. And so as far as we know, that's how black holes are formed. Then they grow by either merging with other black holes or by matter falling into them, and they build up like that. There are still puzzles as to how on earth we grow the billion solar mass black holes, because in certain ways there isn't time for them to build up that large, and that's currently a frontier question in astrophysics.
Research at this level seems to most of us almost unreal. How do you approach these cosmological questions?
I feel that serendipity is very important in science. And serendipity in the sense of Pasteur, that chance favours a prepared mind. Okay, and other people have said what's the most exciting thing in science is not saying eureka, but actually saying that's strange. And the thing is, we get lots of that's strange almost every day, and usually it's because somebody's, even yourself, even me, have done something wrong. But sometimes you get things that really don't fit, and that leads to important things. But you need to have your mind prepared to know what's right and what's wrong and what shouldn't be there, to be able to work out what's funny.
What are the big questions today?
There are two very large questions. What is dark matter and what is dark energy? Most of the mass in the universe is actually dark. We don't know what it is. It could be one small particle, it could be lots of particles, it could be lots of primordial black holes. I don't know. We don't know what it is. All we know is we can feel the gravitational effect, but we can't actually detect it. It doesn't interact with electromagnetic radiation or have any electric or magnetic form. There are things we know exist in the universe, or maybe we're wrong about that, maybe they don't exist, but they're really big questions. Most of the matter in the universe is made out of something which doesn't interact with us other than through gravity. What is it? And somebody might tell us next week. They might not tell us for 100 years.
Ladies and gentlemen, will you please welcome your 2020 Astrophysics Laureate, Andrew Fabian. Thank you.
I think we have to say congratulations first.
Absolutely, absolutely. Let's talk a bit about you and black holes then. You know, astrophysics is a very big area. Why black holes? What got you into it?
I wanted to do space astronomy. I'd been an amateur astronomer when I was a schoolboy, and I decided I wanted to do space astronomy, which meant for me X-ray astronomy. And X-rays were starting out in terms of discovering black holes and things. And I decided that they're very exciting. Lots of unanswered questions about black holes.
That's what's nice about it, I think, isn't it? It's the people don't know the answer. It's that curiosity again, isn't it?
Yes, yes. And, you know, early on is, for example, Cygnus X1 was discovered in the very early 70s. And I remember all of that. And X-rays and optical astronomers and radio astronomers all made a part of the discovery, but it was still called a candidate black hole. And one of my early papers was trying to debunk it being a black hole by saying this thing that was going round a large supergiant star was not a black hole. It was actually a neutron star and another star. But, you know, that's one way of making progress in science, is making things you can disprove.
Absolutely.
And indeed, it didn't last very long.
Where do you even start? How do you start looking for a black hole?
Yeah, that's a really good question. And let's go back to the 1780s when John Mitchell, who was at Queen's College, Cambridge, although he was by then, I think, a rector in Yorkshire, he was the first person who really came up with the idea of a black hole and said the escape velocity from the sun is 600 kilometers per second. The velocity of light is 300,000 kilometers per second. And just using Newton's laws, physics, gravitation, if you pack 100 million stars together, it will have an escape velocity of the velocity of light, so you can't see it. And he then answered, how could you tell it was there? You'd look at its gravitational influence on the surrounding stars and gas. So that's how you do it. It's the effect it has on its surroundings. In particular, gas that's falling into it becomes extremely bright because it falls very fast. It goes up to half the speed of light as it falls into a black hole. If it collides, it gets very, very, very hot. Yeah. And that's why you need X-rays to see it. Also, say that the gas comes from a neighboring star, that star will be swinging round the black hole. So you can look at that star in the optical band and measure the Doppler shift and work out its velocity. That's how people knew about Cygnus X1. But then we know about such things in the galaxies, the supermassive black holes with millions to billions of solar masses. It's the effect they have on all the stars around them. And there's been this exciting results recently of actually making images of them. But that's bringing us right to now.
Yeah.
It's the effect they have on the surroundings.
Amazing. Absolutely amazing.
And is that your instrumentation helps find that, does it? Or is it something else? I mean, so you're looking at it, what kind of instruments are you using?
X-ray telescopes, but we also, for getting the results in the optical, the Hubble Space Telescope, which we just saw, looking at the stars in the optical band, but also radios played an enormous part in this because of the fact that in the matter falling in and churning around, you get strong magnetic fields developing through turbulence and everything swirling around, and they produce jets that squirt out of them. And I would say we don't exactly know how the jets squirt out of them, but they squirt out a matter at almost the speed of light and generate a lot of radio waves. Mm-hmm. So there's all wave bands involved from radio through gamma ray in studying black holes. They're very rich in observational phenomena, many parts of which we don't fully understand.
Yeah.
So it's a wonderful area of research, and if any young people are watching, this is a great area to get into to try and apply physics to how does the universe work.
Do you use the ALMA telescope, the Atacama Large Millimeter Array telescope?
Indeed, I've been involved with the ALMA telescope, which is right up high in the Andes and works in the sub-millimeter band, as you say. It gets exquisite angular resolution. It can look at very fine detail, but also in some of the objects I look at, the biggest black holes, they're surrounded by massive dark gas clouds, molecular clouds, which can be best measured with their emission, the carbon monoxide emission, which is detected with ALMA. So yeah. I'm involved and have worked with, I can't say I've analyzed data from everything. I have collaborators who do a lot of the analysis, but it's just lots of different ways of looking at things.
Yeah.
I think we should not sort of, I say I'm an X-ray astronomer, but I also enjoy optical and other astronomies. And it's wonderful the way we've got such a lot of instruments around the world. It's very much an international subject where there are telescopes in Hawaii and in Chile and Australia and the like, which we're using. Also a lot of satellites above, which are being launched by space agencies, not just NASA, but the European Space Agency, the Chinese Space Agency are starting to do that. It's very rich.
Yeah, yeah. And a lot of really nice collaboration, like you say, between X-ray, radio, gamma ray astronomers and
Indeed.
engineers. We all collaborate together now, which I think is great.
Yes, yes. And sometimes with black holes, there are flashes come from them, because sometimes a star will fall into what we call a quiescent black hole. A black hole at the center of a galaxy can have little gas going into it, but then a star falls into it, and the star is torn apart by the tidal forces, and that produces an event, a flash in the sky, which can be quite bright and is observed by optical astronomers, ultraviolet, radio, X-ray, and sometimes gamma rays. And everybody piles in at the same time to look at them.
I mean, I don't know about the audience, but it's mind-blowing. A star falls into a black hole and it's ripped apart by tidal forces. I mean, it's just a fabulous concept and idea you can't get your head around. But when you first started this, Andrew, what was known about black holes at the very beginning of your career compared to what's known now?
It's just incomparable. It's an enormous amount of information is known. I think what we knew back then, they were very much theoretical concepts, right from when Einstein came up with his theory of general relativity in 1915. He didn't think with his equations there was a simple solution to them. Schwarzschild, the following year, actually made the first simple solution, which was the solution for a black hole, although he didn't really realize what it was. And it was something that nobody thought much about until the early 1960s. And then in 1962, 1963, there was the discovery of quasars, and there was the solution for the spinning black hole by Roy Kerr, and tying quasars together with black holes was something that the first Kavli Astrophysics Prize was given to Martin Schmidt, who discovered the quasar 3C273 using positions given by Cyril Hazard from UK, and then also at that time, then Donald Lyndon Bell, who was the other prize laureate, Kavli laureate, he came up with a theory of how the material swirls around the black hole to produce the radiation which powers the quasar.
Huh. And you've got much more information now, I guess, about how black holes, what their place is in the ecosystem of the universe. So tell us a bit about that, because that's also fascinating.
Yes, as I said in the piece we saw earlier, that for a long time black holes were thought to be possibly in some galaxies, at the centers of some galaxies, with some people thinking they might be in all galaxies, but we didn't really know. And then they started to be seen at the centers of galaxies, detected, and it became apparent that they were generally there. But as I said, people saw them rather as a sort of ornament there. Yeah. And what happened in the 1990s, and I got very excited and worked on it, was why there was this connection then seen between the mass of the black hole and the mass of the galaxy. They seemed to be linked. There was a strong, there's a factor of 1,000 between the mass of the galaxy and the mass of the black hole. Why is it like that? And initially, most of us thought it was due to the mass of the galaxy clearly determines the mass of the black hole. But then what we realized, it was the other way around. It was this tiny object in the center, tiny, tiny, tiny object, a billionth of the size of the galaxy, that was controlling the whole galaxy. It controls the mass of the stellar part of the galaxy, the part that we can see with optical telescopes. Yeah. So this was a sort of overturn of what we were thinking, and black holes jumped then to being a key part of the universe in determining what we see there. And I don't think we've finally explored what their role is. Only now are we starting to realize they not only influence the galaxy, they influence the surroundings of the galaxy, and it may be even larger.
So what is it that how do you start? What's the sort of 101 of black holes? Because it's almost like you don't know what you don't know. So how do you start to try and observe a black hole?
The work has been a sort of random, it would appear almost a random walk, you're sort of going around. And one of the things that's ill appreciated about science is trial and error is enormously important. The trouble is the funding bodies all assume that they'll fund you for definite progress along a line, right? But actually, I think most laureates would agree, it's sort of a bit like this, you understand?
We just heard lots of mms and nods there, yes.
But you have to go. So it's taken time, a lot of time and a lot of false starts, but I think we have gone through this. And if you want to observe a black hole, you can get a small telescope and you can see a quasar. There are lots of quasars out there, billions of them out there, and so you can see them. But then to interpret what you're seeing and connect it with the black hole, because bear in mind, the black hole emits nothing, okay? You're seeing the influence it has on the matter immediately around it, but you can't see the black hole. The black hole's black. You can see what's its matter swirling around it and so forth. And that can be extremely luminous. It's the most powerful source of energy short of matter-antimatter annihilation, okay? If you took that water and tipped it into a black hole, you would get more than 1 billion times more energy out than you would if you had that mass of petrol and just burnt it. Okay, you're getting at the structure of matter itself, not just chemical reactions or even nuclear reactions. You're using the matter itself.
Mm. And we wonder why black holes are the subject of so much fiction, science fiction, films, movies.
Indeed.
Why we have in science festivals queues round the block to hear about black holes.
Yes.
It's extraordinary, isn't it? And yet the huge public interest isn't matched by the astronomy funding. So we'll have to have a plea here for more astronomy funding.
Do we need a soapbox?
Yes, more astronomy funding.
Yes. I think it really is curiosity-driven research. And I don't think it has any social aspects. Many other branches of science, have, implications. It's going to solve this problem or that problem. I can't hand over heart say, give me money for astronomy and we'll solve some problem that will result in a widget in the supermarket or somebody cured of something. you never know, it might do, but this is pure curiosity-driven research. It's the funding for it, I think, should continue, and it draws young people into science, because children start off curious, and their curiosity is usually strangled out of them before they become teenagers, and many of them lose it during their teenage years. If you can maintain the curiosity by things like black holes and astronomy, I think, hooray, and then they may go on to be scientists. And we've seen in the pandemic how important science is, and it was mentioned by the speakers earlier. Science is really important to humanity, and I think science is powered by curiosity-driven research. And unfortunately, funders don't understand that.
Yeah.
That is an absolutely perfect way to end this conversation with you, Andrew. And I have to tell you that our audience have been hanging on every word. And you hear about this stuff, and immediately you want yourself to go and find out more. And that's what astronomy does for us. And it's on such a vast scale. Thank you so much for telling us about this. Congratulations again.
Thank you so much, Andrew. Thank you. Thank you.